Well, good evening and welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here. It's great to see some familiar faces and some new faces as well. For those of you that came here, you'll notice that we are doing some major construction outside. We're finally, after 30 plus years, giving an opportunity to replace our parking lot, with many thanks to the to Broome County, who is helping us underwrite that. And want to welcome those that are watching on our live stream. And it's been great to be able to do this live stream. And literally, we are reaching people around the world. Very often, we'll get people from Europe, or in fact, often there's this person in Australia probably having their lunch Saturday morning there. Anyway. Just a matter of interest, who's here for the first time? All right, fair number of people. Okay, good. Who here are members? Okay, the rest of you. Okay, very good. For those people that raise their hands first, the people that raise their hands second have a bit of information that is pretty important and valuable, and that's Kopernik membership. We are a nonprofit. We're an informal STEM education center, but we do, our membership is particularly useful because we belong to an association called the ASTC, Association of Science and Technology Centers, and with a Kopernik membership, you can get into over 350 other science centers. You can go to the Robeson Museum, you can go to Museum of Science and Technology up in Syracuse, or the Franklin Institute in Philly, or the Intrepid down in New York City. So if you like this kind of place and you're not a member, you may want to consider joining us. Our website tells us a lot of what's going on, so we always mention what's going on. So tonight is our talk about doing some deep sea diving for fossils. We have a Red Cross blood drive coming up, and also June 3rd we're doing Rocket Fest, and this is where families, but even adults, will build those Estes rockets. Then you come up and we'll give you a launch window, and you come up and we'll check out your rocket, make sure that it's ready to fly, and put the engine in, and then you get to go outside, and either you or your child gets to hit the button that sends it skyward. And some of the rockets actually will go over 1,000 feet, and we get almost all of them back. So that's always another good thing. Again, for those with school-aged children, we also have a very extensive summer camp program. So where am I? Here we go, summer camps. Actually, a number of them have already filled up, but it's been a great opportunity for kids to come up and sort of continue their summer learning and doing it while having fun. I mentioned earlier that we do live stream, and so back in March of 2020, we were doing a Friday night program, and then COVID really basically shut everything down. So we said, all right, we'll just sort of put everything on hold for a couple of weeks until this thing blows over. well, that didn't quite play out that way. And so by May timeframe, we decided, look, we have all these speakers lined up. Why don't we do something with them? So we got them to zoom into here. We then turned it back around, put it out on our YouTube channel, and now we have over 13,000 subscribers, I believe. And so we do all of our Friday night programs with live stream, but also we do observing sessions. So we've done, in fact, actually, it was just about a year ago that there was a lunar eclipse in May. And at one point, we had over 25,000 people watching our live stream. In fact, some people in the chat said, you know, we left the NASA's live stream because we like yours better. And that's actually all due to Jeremy Carty back here in our live stream. He's our live stream astronomer and does just a fantastic job. So we've actually got a couple of observing sessions coming up. There actually will be a partial eclipse in October that will maybe cover a 30% solar eclipse here. So we'll have an event here, both in person, but we'll also do that on live stream. And then, of course, in April of next year, there'll be an eclipse that's coming up up into New York State. Actually, here at Kopernik, we'll be about 99% covered. You'd have to go up to Syracuse or Rochester or Buffalo to be in totality, but we'll have a good time with that. One of the things we do is, the rule here is that you cannot leave Kopernik until you look through a telescope. And so we're going to enforce that tonight. Fortunately, we've got some clear skies that are going to be, that have been granted us this evening. Also, this evening, we're going to be able to see a Starlink train. Actually, last night, Kopernik was down and joined the Binghamton Philharmonic at the Anderson Center for their May the 4th Be With You concert series. And so we brought some telescopes down, and we were out showing people the moon after the concert. And there are these series of lights that just came by. It turns out, actually, yesterday morning at 3 in the morning, SpaceX launched 50 of these Starlink satellites. There'll be another pass of those about 9:38 tonight. So you just have to be finished by 9:38. Okay. Or else, if you have to continue, what we'll do is we'll stop it, go out, watch them go by, then we'll come back and finish up. But so anyway, it'll be an opportunity to see something that most people don't get a chance to see or don't really understand. They think it's UFOs. Well, they're only U's if you don't know what they are, right? So anyway, so let me see. I think so our YouTube channel. Getting back to that, these are the ones that are coming up, but you can also go back and look at previous talks and previous. I'm trying to think here if there's a good one we can show here. Here's the total lunar eclipse in May.
Giddy up! Let's get right into it.
How
do you make money using artificial intelligence?
So this again was the lunar eclipse that Jeremy covered here, and what he did was he did a time lapse. Yeah, of course. There we go. Thank you, YouTube. And what's interesting is when we finally get into total eclipse, then he'll change the exposure so that we can actually get that blood moon kind of look. And then you can actually start seeing some other stars as time goes on. And then finally it'll come out of total eclipse and then brighten back up again. And just about there. Anyway, so I think you get a sense of the kind of stuff that is available on our YouTube channel. So check it out. If you're unable to make the Friday night program and you really wanted to see it, or you wanted to see this program again, it'll be on our YouTube channel. And then finally, as I mentioned, we have that Starlink train that's going to come by, and it's let me see here. It says on May the 5th, it'll be going from west to east, starting at 9:38. So we do these Friday night programs as a benefit for being a member, but also it's really, we're trying to promote lifelong learning. And although we actually had a bunch of first graders in here today, but ultimately, we should be learning our entire life, and this is really an opportunity to sort of to feed your brain. And so, although we do astronomy very well here, I like to make sure that we cover more than just astronomy, and tonight that's going to be one of those things. So, Adriane Lamb is a fairly new member of the astronomy department, well, compared to some of the other members that are there, and she was excited about coming up here and talking about the research that she does. And so we are going to go to her presentation. We'll hit F5 and turn it right over to you, Adriane.
2 clicks.
On this one?
No.
Yeah.
All right, there you go.
Oh, thanks. I'm not used to this technology, even though I work with technology. Okay, let me just make sure this is going to work. Oops. Awesome. Okay, so I am really excited to be here, so I want to thank everyone for having me here and inviting me. This is really exciting. My husband and I moved up here in August 2019, and I started as a postdoc at Binghamton University in January 2020. And then COVID hit, so everyone had to stay home. I couldn't do research, and I didn't really get to know people in the community. This is my first time being here, so I'm really excited. So I am going to speed through the talk, so we can go look at stars and stuff. We're going to be looking up at the sky tonight, but today in this talk, we're going to be looking downward into the oceans, and I'm going to be telling you about the ocean sediments. So I'm a new assistant professor at Binghamton University in the Earth Sciences department, and what I specialize is in paleontology, so I look at fossils to answer questions about our Earth system. But I also use the sediments collected from the bottom of the seafloor to also answer questions about our Earth. So I go out on these big ships, and we sail at sea for 2 months, and we collect these sediment cores from the seafloor, and then we do research on them. So that's what I'm going to tell you about tonight. So the program that I sail with is called the International Ocean Discovery Program, or IODP. And I'm going to tell you about Expedition 371. They all have a number. And we sailed on this in 2017. And I'm going to tell you a little bit about the history of scientific ocean drilling. It dates back pretty far, and the cool things that we've learned from that and the technology. I'll tell you about Expedition 371 and the motivations from drilling in the Tasman Sea between Australia and New Zealand. I'll show you some major findings from the expedition, tell you some cool stories while we were at sea. And I'll just wrap up really quickly, leaving off like the science that we're doing right now at Binghamton University. So this is an actual picture from the Tasman Sea when we were sailing. The seas are very choppy, they can be very rough. But this was after a storm. We had this beautiful double rainbow, so there's incredible, incredible views there. So let's just start with a brief history of scientific ocean drilling. So the picture in the background of this slide is what we call the moon pool. So on the ship, there is a hole in the middle of the ship. And it's about 10 meters across. It's not too terribly big. And that big pole that's coming down in the middle is our drill string. So that's the pipe that we put down to the middle of the seafloor, how we collect sediments. And I'll talk a little bit more about that in a minute. But first I want to just start off with like what is scientific ocean drilling. And basically, in a nutshell, we take these big ships that are equipped to drill sediments from the seafloor. So they have this coring technology, and we sail them all across the world. And on these ships are technicians, there's scientists, there's support staff, drillers, and the entire goal of these expeditions is to recover sediments, but also rocks from the seafloor and study them in more detail. There we go. So there's 2 main purposes of scientific ocean drilling, which we just abbreviate as SciOD. There's the scientific objectives, and then there's a societal objective. So within science, we want to investigate the ocean and its atmospheric responses to past climate change events and relate that to what's happening today or in the future. We also want to decipher tectonic activity, so plate tectonics. How does it work? We also want to infer evolution and speciation events, for example, in these marine plankton that I study, and how speciation proceeds in an open marine environment, and how these plankton and these organisms respond to climate change of the past. On the societal part of scientific ocean drilling, we want to train the next generation of scientists. So that's part of my job at Binghamton. I have a lab full of undergraduate to graduate students. I'm getting 2 more PhDs in the fall. So really growing the lab group and training them to also become educators. The second point is to educate the general public. We want to share our science with the public, so everything that you're seeing that I'm presenting on, the scientific ocean drilling, it's all funded by the National Science Foundation. It's all taxpayer dollars. So you all should have access to that data, and we should make it understandable. So this is what I'm doing today, is public outreach and education. And we also want to connect with policymakers. So the data that we're finding, the scientific findings, these are really important things to communicate to our policymakers, because we hold the keys to understanding climate change in the past and how our Earth system works and will behave to increased warming, so that they can make informed decisions. So scientific ocean drilling has a really incredibly funny start. It started back in 1958. So in the 50s and late 40s, a bunch of guys got together and they were like, hey, wouldn't it be really cool if we punched a hole in the Earth's crust? And wouldn't it be really cool if we didn't just go through the entire crust, but then we punched down into the mantle, so that layer of the Earth that's under the Earth's crust, where all the continents and the oceans sit? And they were like, yeah, that sounds really cool. And I'm kind of exaggerating a little bit here, but this is actually how this story happened in a nutshell. And then their only other kind of complication here was finding funding. They needed money, and to convince people, like, hey, actually poking a hole through the Earth's crust is actually a really good idea. They did find the money to do this, and they did find a drill ship in which they could do this. So they got this oil drill ship. It's called the Cuss-1, and it was, you can kind of see it has this kind of derrick feature on the top of it, and that was made for drilling. It was made for drilling oil, but then they retrofitted it to drill sediment cores. So they went out into the ocean, and they did drill. So they were trying to hit the Mohorovic discontinuity. It's the place in the Earth's crust where we transition from the crust that's very cold and very brittle to the mantle where it's more warmer, where we have deeper rocks. It didn't go as planned. They only made it down to about 600 feet. But they recovered sediments that were of Miocene age, about 23 million years ago. And there's been some really drastic climate change events that have happened over the last 23 million years, and they recognize that those sediments that they recovered, by the sediments themselves and the types of sediments, the color of the sediments, and the fossils contained in those sediments, that those sediments were actually really incredibly important to science and could tell us things about Earth's past. So Project Mohole went on until 1966, and that's when the project ended. However, because this program was so successful and they found such scientific interest from drilling these sediments, this started a program called the Deep Sea Drilling Project, or DSDP. So this was from 1968 to 1983. And they did away with the Cuss-1 drill ship, and they got this ship called the Glomar Challenger. So this was a true drill ship for sediment cores. It's a ship that's kind of like a floating laboratory. Scientists could live and work on it at sea for 2 months or multiple months at a time. It could drill sediment cores from the seafloor, and it could drill pretty deep. So from 1968 to 1975, this was a solely US-funded project. We were the only ones supporting it financially. But this project started to gain international attention. In 1975, it's when Germany, Japan, the United Kingdom, the Soviet Union, and even France, they then joined onto the program, so they started pitching in money and funds to also go out and sail. And because they pitched in money and funds, their scientists began to sail with ours as well. So what really came out of the deep sea drilling project, one of the third expedition actually that sailed, is they drilled sediment cores in the middle of the Atlantic Ocean, where there's actively like seafloor being made at the mid-Atlantic ridge. They proved the theory of seafloor spreading in plate tectonics, which is something that was just a big hypothesis at that point. So that was a really big finding. In 1985, this program switched over to the Ocean Drilling Program, or ODP. So this lasted until 2003, and this was a truly international effort. Approximately 17 countries joined into this effort, so they funded the project, and their scientists also sailed. It was also at this time when we got a new drill ship called the Joides Resolution. So that's the Joides. It's the one that we sailed on, and I'll talk a little bit more about it in a little bit. But then in 2003, the program switched again. It switched names. In 2003, it was the Integrated Ocean Drilling Program. So it was really during 2003 to 2013, during this one decade, IODP really employed new drilling strategies, so we could drill deeper into the Earth's crust. We could recover more sediments and more rocks. It was really, really great. And then in 2013, the program changed name again, and it's now the International Ocean Discovery Program. So this program ends this year. Unfortunately, it's not going to be refunded. NSF is cutting our fundings, and the ship is going to be taken apart, which is pretty sad. But IODP is really, really successful. We have about 24 partnering countries that participate in scientific ocean drilling. So scientists from all over the world live and work on that ship and work together to do science. It's really neat. But IODP today is different because we don't have just one ship. We have multiple drilling platforms. So this is what IODP looks like today. We have mission-specific platforms, or MSPs. So that's the image in the upper right of the screen. So these are platforms that a ship will go out and kind of sit in the ocean and put the legs on, and you basically just drill sediment cores in one place. You can't really move around a lot. It's really useful when you're drilling into really shallow water environments, like really near the coastline or off the coast of, we actually used that a few years ago to drill into the Yucatan Peninsula off the eastern coast of Mexico, where the Chicxulub impact crater hit. That's what killed the dinosaurs 66 million years ago. In the middle of the JOIDES resolution, that ship is operated by the US, so we have control of that ship. And the Chikyu here at the bottom is operated by Japan. So the difference between the JOIDES and the Chikyu is that the JOIDES can drill in about 4 miles of water before it hits sediment. It can drill down a little bit more. But the Chikyu is made to drill really deep, and it's also made to drill hard rocks. Really cool. We're going to focus a little bit on the JOIDES resolution because that's the ship I sailed on for this expedition. It's the one that we've been using for quite a long time now. And it's the one that will sail into next year after the program ends. So what you're looking at now is a map. And this map of the world ocean and all these dots are all the places that we've drilled in our oceans today. Each of the different colored dots corresponds to the different programs of scientific ocean drilling. So DSDP, for example, is in the green. So you can see on this map at a very kind of preliminary level that there's some places in the ocean that have been drilled a lot, and there's some places in the ocean that are a bit more neglected. And there's reasons for that. So for example, in the North Atlantic, we have intensive drilling. It's close to us, right? We're right here off the East Coast. It's easy to access. International waters, no big deal. We can kind of get there. Along the coast of, around Japan is really a hot spot to drill because they have a lot of volcanic eruptions going on, a lot of earthquakes, so they really want to understand that region. And you'll notice that there's places where we don't drill, like in the Southern Ocean around Antarctica. And part of that is because we have really long or really strong currents there that we just can't really drill within. It's kind of hazardous. And we don't really drill in the Arctic Ocean, and that's because there's ice there. But that ice has been melting back as the Earth warms. So there's some expeditions that are actually going to sail off the coast of Greenland, and that's the last expedition that's actually going to go. It's going to drill off the west coast of Greenland. But what I'm going to tell you about today are those 6 pink dots that are circled with that pink circle between Australia and New Zealand. So that's where we drilled on IODP Expedition 371. So I'm going to tell you a little bit about this expedition and kind of the motivation for it and why we were out there drilling in the middle of the Tasman Sea. So in 2017, there was a new paper published by Nick Mortimer and his colleagues. So Nick is a scientist at GNS Science. It's like the United States Geological Survey of New Zealand. And what he did was formally name and recognize a new continent called Zealandia. So this is an image from his paper. Zealandia is down here. So New Zealand is in the dark gray, but Zealandia is outlined in the lighter gray color. So they recognized it as a continent. And this paper was published right before we sailed. So we were actually going to drill sediments from atop this newly named continent of Zealandia. We did not plan it so that the paper would come out and then we would sail. But it actually worked in our advantage because it got a lot of hype and a lot of media attention around the world. It's not every day that we define and find a new continent. So this was really kind of a big deal. And then we were going to go out and drill it. So it was really, really a cool opportunity. We got a lot of attention. I'll talk about that in a minute, but let me just focus on Zealandia for a minute because it's actually a really cool continent. So on the left side of the screen is that figure from Mortimer's paper. And you're looking again at Zealandia. You can see how close it is to Australia. But if we zoom into it, so what you're looking at now is a bathymetric map of around the Southwest Pacific. So we're looking at water depth. So the cooler colors are where the water is, but then the warmer colors and the greens are where there's land. And Zealandia, the official outline of that continent, is outlined in the red dashed lines. So Zealandia is a continent that's so different from others because 94% of that continent is submerged underwater. That's not common for continents. The entirety of Zealandia encompasses about 4.9 million square kilometers of continental crust. So the continents are made of a different type of rock than our oceans are made of. It's silica rich. Silica is a very light mineral. It's basically quartz. That's what Zealandia is made of. And we know that Zealandia, the bounds around here, even though it's sunken beneath the waves and it's down on the seafloor, we've done, or not me personally, but other scientists have done drilling around here. They've done dredge samples where they take a boat out and drop this big bucket off of it and just dredge the bottom of the seafloor, and then look at the rocks that are there. They've also looked at rocks on New Zealand and New Caledonia, and all of these rocks indicate that Zealandia is actually continental crust. It's not oceanic crust, so it is a continent that was then submerged beneath the waves. And you're probably wondering, well, how did this happen? So I'm going to tell you a little bit about Zealandia and how it formed. We're going to start this story way back in time, 390 million years ago. So this is what we think the world looked like during this time. So we had a lot of the continents that worked together or conglomerated, and we called it Gondwana. And there was also, this is like ancestral North America, we called it Euromerica. Australia and Zealandia were over here on this other side of the landmass. Now we're going to fast forward to about 83 million years ago to the Middle Cretaceous. So this is about 20 million years before the dinosaurs went extinct. So this is what the Earth looked like. You can see North America is up there in the corner where it approximately is today. Sea level was very high because there's no ice caps at the North or South Pole. And here's where Australia and Zealandia are. They're located very close and actually attached to Antarctica. So the continents began rifting, or I should say, Australia and New Zealand began to move away and kind of rift apart from Antarctica, so they kind of started to tear apart from one another, around 83 million years ago in the Middle Cretaceous. And then if we fast forward to the early Eocene, so this is around 50 million years ago, those continents had continued to move apart. So you can kind of compare these two images and see that up here in the Eocene, Australia and New Zealand have now moved and disconnected away from Australia. So the continents are coming into their more modern day configuration. Now we're looking at a modern day map of kind of the Western Pacific Ocean. So there's Japan, Australia, and here's New Zealand and Zealandia down here. And I've got a few things highlighted on the screen. So it was around 50 million years ago during the early Eocene, so when the world looked like this. The Pacific Plate is this major plate in the Pacific Ocean, and it has, here's Hawaii, here's the Emperor Seamounts. We noticed this major change in plate motion. So the plate was moving this way, and all of a sudden it changed direction really quickly and started moving that way. So what happened here is that this ocean crust, when it moved that way, so you can see my arm kind of moving this way, it put pressure on the continental crust down here, and it also formed this Marianas Trench over here off the coast of Japan. So we think this whole, this ring of fire, if y'all have heard of that, it really started to form during this time with this change in the plate motion in the Pacific Ocean. Okay, so we're looking at two major zones where the ocean crust is being subducted or sucked back into the Earth. Here's the Izu-Bonin Marianas Trench, or the Marianas Trench as we know it. It's one of the deepest places in the ocean today. And here's the Tonga-Kermadec subduction zone. Again, it's another place where that ocean crust is being sucked back into the crust of the Earth. And it's moving back under Zealandia. So that's what we're kind of looking at. So one of the objectives of our expedition was looking at how these zones form. How does this ocean crust that's just sitting here begin to form and then start to get sucked back into the ocean or sucked back into the Earth's crust? We're not really sure actually how that happens. So there are a few outstanding questions related to plate tectonics and also ancient climate in this area. We know that subduction zones, these places where these continents and ocean crust get sucked back into the Earth's crust, they drive plate tectonics, so the creation and destruction of ocean crust and continental crust. But we don't exactly know how and why these things happen and how they start. There's another thing that we're not sure about. In the Tasman Sea, in the seaway between New Zealand and Australia, we're actually not sure what the ancient climate was like tens of millions of years ago. What you're looking at here is a figure from Hollis and others in a paper they published in 2012. And what they were trying to do is look at sea surface temperature during the Eocene, so this was about 30 million years ago, and what the temperature in the ocean may have looked like. So all of these numbers here are temperatures in degrees Celsius. You can see between New Zealand and Australia here, there's a big question mark. That's because we actually don't have any data from that area of the ocean. We actually don't know how warm it was. Further, there's a big mismatch between some of the data that we do have and some of the data from these climate and ocean models. So some of the temperature is yielding surface temperatures about 5 to 10 degrees Celsius warmer than predicted by ocean models. So there's like a really big mismatch between what we think the temperatures are there. So we needed to figure that out too. So the goals of Expedition 371 were to kind of address head-on these two unknowns. Related to subduction zones, we wanted to investigate the processes and the timing of the subduction zone and that Tonga-Kermadec subduction zone. When did that start and how did that start? That was one of the major questions we wanted to answer. The secondary question was, we wanted to actually constrain the temperatures, the sea surface temperatures in this area from tens of millions of years ago so we could further understand ancient ocean conditions in this region of the world ocean. So we needed to recover those sediments from the seafloor so that we could then use the fossils, the chemistry from those fossils to then do this. So to accomplish those goals, what we did was drill 6 sites in the Tasman Sea. So here again is just this bathymetric map. It's showing you water depths with the very cool colors are deep waters, and then the warmer colors are more shallow areas. So you can see around Tasmania, it's very shallow. So there's Australia, again, here's New Zealand, New Caledonia, but here's the bounds of Zealandia. So we drilled 2 sites in what we call Lord Howe Rise. It's this very shallow kind of area right here. We also drilled 3 sites in the basins close to the Tonga-Kermadec subduction zone. And we drilled 1 site in what we call the abyssal plain. So that's outside the bounds of Zealandia in very, very deep waters. And that site's really cool. I'll show you a little bit about it later. Okay, that was a lot of science. Let's take a break now and just talk about sailing and how we start this expedition. So when we sail on these expeditions, what the scientists do is they meet beforehand online, on Zoom, and they talk about the mission, the goals, and like projects that people are going to do. Then when it's time to sail, all of the scientists meet in the area, the port city that you're going to leave from. So we met in Townsville, Australia. We all flew there. And that's where we boarded the Geology's Resolution. That's where we left port. This is really cool because IODP has the money to pay for scientists to fly out to this port city, and then they will fly you back home. And they'll also pay for your hotel. So it's actually a pretty sweet deal. You really don't have to pay for anything. You're just there to be a scientist, and they're like, yeah, we'll pay for it, go. It's like the best thing ever. So my husband and I took full advantage of this. So we had not been able to go on our honeymoon because I had been doing my PhD. It was very busy. You know, honeymoons are expensive. So we actually leveraged that, and we left a week early to go to Townsville, and we stayed on a little island called Magnetic Island for a week before I sailed, and it was awesome. So we dove around the Great Barrier Reef. That's us diving. We saw some whales breaching on the way back. We saw a koala family. Our Airbnb hosts were amazing. They took us around the island. Flying fox bats. They're just incredible creatures. I'm really into brachiopods. I'm an invertebrate worker too, so I was like really thrilled to find these organisms, and my husband could not have been less impressed. I was disappointed in him. Sorry. So then when it's time to sail, we went back to Townsville, and then I met up with the scientists. So what we do, we stay on the ship in port for about 2 days. So the reasons for this is we want to get to know the other scientists. So we're sailing with these people for 2 months. That's a long time at sea to be confined with the same 30-some people. So you want to get to know them, the staff and the crew that you're going to be rooming with. We also got our room assignments, so everyone stays in a room with one other person. And it's not bad because we're working 12-hour shifts. So if I'm in the room, my partner is working. When they're in the room, I'm working. So we just kind of like ships passing in the night. We also learn our way around the ship. It's a big ship. We have to find our way around. There's several floors to the thing. We're not used to that. So we just want to get a feel for living in this space, and also starting to learn our lab equipment and how to run that equipment so that we can do the best science that we can while at sea. So everyone gets a name tag. That's me in front of the Geology's Resolution. I couldn't have been more excited. What's really neat is that we have these crossover parties. So when the Geology's Resolution comes into port, there's already a team of scientists on there. So they get off the ship, and before we get on the ship, we have what we call these crossover parties. So it just so happened that before we got on the ship, there was this program going on called School of Rock. And School of Rock is when we get a bunch of teachers, so K-12 teachers, onto the ship, and there's other scientists that train them about scientific ocean drilling and how to do science. So it turns out my PhD advisor, Mark, he's right there, was sailing on that expedition, so he met me in Townsville and we hung out. And there's some other good friends in that picture as well. So here's my PhD advisor, Mark. That's my friend Joita. and her PhD advisor, Jerry. It was Jerry and Joita were sailing. So it was really, really fun to be there with my PhD advisor. It kind of felt like a handing off of the reins type thing. It was pretty special. But then it was time for us to leave Townsville. So these are just some pictures from that morning. So we left early morning, and it was beautiful. The port waters were very smooth, almost smooth as glass. We couldn't have asked for better conditions. Beautiful sunrise. This is us leaving port and looking at Townsville in the back, so you get this beautiful view of the mountains and the landscape. Just incredible. Some more pictures of us. These are the scientists. We're all on the top deck of the Geology's Resolution, just kind of looking out. It's really cool because everyone just gets so excited. You can kind of feel it. And these are some of my shipmates. So you can kind of see we're up on this upper deck. There's a lower deck and then one more down here. And this is another funny story that I always love to tell. So when my husband and I had gone to the Great Barrier Reef, it was a day trip. And then my PhD advisor, Mark, said, well, we're going to go out there the next day. Maybe we'll still see you leaving port. And I was like, I doubt it. So we were leaving port, and then I had my big telephoto lens with me and my camera, and I noticed this little ship shoot out of port. I was like, what the heck is this? And then I noticed that this thing was coming towards us, and I realized, oh my gosh, that's my PhD advisor with the scientists. They're going to the Great Barrier Reef, and I'll bet they've told the captain to fly by the Geology's Resolution so they can wave to us. They were. So that's my PhD advisor with his hat on backwards, hanging on, waving. And some of the other scientists that were on the Geology's before we got on it. And they got awesome pictures of us. I got a picture of them. Again, just a very cool moment. It was very neat. So Mark's an avid photographer. He got this wonderful picture of the Geology's Resolution. Here's all the scientists at the top here where I showed you pictures of hanging out because we're all excited. Mountains in the background. So on the ship, though, I want to show you, kind of point out some things. So the Geology's is, again, a floating laboratory, and it's a place where we live and work. So this part right here is where all of the captain and the crew live. The scientists live down here, so when we're in our bunks, we're actually underwater. So in the bottom part of the ship. There's also kind of there's a mess hall where we all come together, and there's also crew quarters back here as well. All of the laboratory spaces are kind of back here. The middle of that ship, that really tall part, is called the derrick, and that's where we have the drill string. So the derrick stands about 62 meters above the water surface. So it's about 5 stories tall. It's big. So that's where we do all the drilling, where all the action kind of happens. The catwalk is in the back. That's where the cores go when they bring them up from the seafloor. The technicians lay them out, they cut them, and then we start to inspect them and do science on them. And then number 3 in this picture is the drill string. So that drill string, that metal part, comes down through the derrick, and we pipe drill string down to the seafloor until it hits the bottom of the seafloor, and then we start drilling. That's when we deploy the drill bit. So we can actually do this drill string. It says 6 miles, but it's more like about 4 miles of water depth that we can drill in. And the Geology's Resolution itself is pretty big. It's about 1.5 football fields long, and we do have a helipad deck on the back in case we need to do an emergency, like someone needs to leave for an emergency. So the drilling technology on the Geology's is called a riserless drill system. So in the oil industry, they use a riser drilling system. This is where they pump like fluids and other stuff down the hole. They cut around the core, and then everything, all the cuttings and the core and the fluids, they bring back up and they capture that. But the Geology's does riserless drilling. So what we do is we just pump seawater down into the hole to help lubricate everything and keep things running smoothly. And there's a bunch of cuttings, but we don't capture the cuttings. We don't care about it. And we just let that seawater that we pump in go back into the ocean. We're not pumping chemicals down or anything like that. And then we just want to recover the sediment cores that we get with our drilling. So this is kind of what this looks like. So what you're looking at now is the derrick that's in the middle of the ship. So that's an image, and this is looking up into the derrick. But what I really want to point out here is this yellow feature. So it's kind of this, it looks like a pipe. But we call it the heave compensator. And the heave compensator is a really important part of drilling. Here it is at the very top up there. This is the drill string, and these are the drillers. So the scientists aren't allowed to touch the drilling, but we have drillers that are dedicated to using this equipment. They're trained in this. The heave compensator is really important because essentially what we're doing, we're in the middle of the ocean and there's always waves coming at us. So the ship's always going up and down, up and down. If you look at the heave compensator, it looks like the heave compensator is going up and down, up and down. But in reality, where the heave compensator is keeping that drill string and the drill bit steady, and we are moving up and down around the heave compensator. So it's really important when we're drilling that we want to keep everything as steady as possible, the drill string and the drill bit that we send to the bottom of the seafloor, because if it's bouncing around the bottom of the seafloor, that drill bit, you're not going to recover good sediments. Oh, and that's the picture of one of our drill bits. That's actually, it looks pretty nasty, like it would tear up hard rock, but that's actually made for soft sediment. But that just gives you kind of a scale of how big these things are. So there's another picture of the derrick, and this is the drill floor. So when you come out of our scientist labs, you're looking at the drill floor. That's called the doghouse. So the Geology's Resolution is one of the only ships in the world left where we do drilling manually. So when you go in the doghouse, there's this massive brake that's sitting there that's hand operated. There's all these controls. So the driller is actually manually controlling the drill bit, its speed, how fast it's going. You can see how fast it's drilling. So they control all of that. So it's an outdated way, but it actually really works well. And this is the drill string. This is where we send the metal piping down into the seafloor. And one floor under that is that moon pool where I showed you earlier on a slide, that big open space in the middle of the ship where we can see that drill string going to the bottom of the ocean. It's also very important that the ship stays very steady while we're drilling. So the ship is equipped with 12 thrusters. So these are the thrusters. This is when they're deployed down. So when we get to the area that we want to drill, we put the thrusters down, and they just kind of hang below the ship. And what they have is like big fans on them, right? So they're keeping us in place. It makes the ship not move any more than about 10 meters space. So it's keeping us very, very steady in the water. When the thrusters are down, the ship doesn't move any more than about the size or diameter of the moon pool. So that's that moon pool. It's the opening in the middle of the ship. And you can see a person, a driller, that's sitting there for scale. It's not that big. So that ship doesn't move out of the diameter of that moon pool. So really incredible technology. Okay, so getting back to on board the ship, we sail with about 30-something scientists, about 35 to 32. And it's really important. There's really limited space on the ship. There's limited resources, so everybody has a very well-defined job. So when I sailed as a planktic foraminiferal biostratigrapher. So that's a mouthful. Let me just break it down. So bio is life, like biology. Stratigraphy is the branch of geology that deals with putting time or age into the rock and sediment record. In other words, I use life to tell the age of rocks and sediments. So I use these tiny fossils. They're called planktic foraminifera. They're really tiny, about the size of a grain of sand, and I use the extinction and evolution events of these little plankton that are preserved in the sediments on the seafloor to tell everyone else on the ship how old the sediments are that we've brought back up into the ship, or where we are back in time. Because the sediments that are right at the sediment-water interface are young, and as we drill deeper, we're going back into time. So we want to know that. I also was a ship invertebrate paleontologist, so brachiopods, bryozoans, things that we find around here in our rocks. Mollusks, bivalves, these are really common invertebrates today. So this is a picture of me on the ship sitting at the microscope in the paleontology lab. There's my colleague Adriane in the background. And I would sit at this microscope for about 8 to 12 hours a day looking at fossils. It sounds miserable, but like I was in absolute heaven. I loved it. It's really cool. So the paleo lab itself contains 6 microscopes. And sometimes we sail with a lot of paleontologists and we all work on a different group of organisms. So I do foraminifera. They live in the surface ocean. The benthic foraminifera live in the bottom of the seafloor sediments. We look at nanoplankton. They're these tiny, tiny, tiny little plankton. And these other things, radiolarians, ostracods, and we even look at pollen that's preserved in those sediments. So every interpretation that we make on the ship relies on us, the biostratigraphers, because without age, without knowing how old something is, you don't really have anything. You can't put it into context. So I want to focus for a minute on planktic foraminifera. They're the loves of my life. Sorry, Jacob. But this is kind of what they are. They're marine protists, so they're single-celled organisms that live in the ocean. There's 2 main flavors. There's benthic foraminifera, those live on the bottom of the seafloor, and there's planktic foraminifera. These are the ones that float in the surface ocean. They produce calcium carbonate tests, the same thing that seashells are made of that you'd find on the beach. And they are photosynthesizers, so they can make their own food, but some of them are actually carnivorous. So there's a planktic foraminifera that's feeding on a copepod. So that's a single-celled organism that is eating a multicellular animal. So it's very, very cool. Planktic foraminifera, these are the species that I work with, have been around for at least 175 million years, and they're still alive today. They occur in the upper about 200 meters of the water column. They have a phenomenal fossil record. Sometimes when we drill sediments, see this like snowy white color? Those sediments are snowy white because they're filled with those fossils, the tests of these ancient fossils. There's just thousands of them that we can recover very easily. So these things are very, very important, again, to date the sediments and say how old the sediments are that we're drilling and recovering, and put all of our findings into a time context. So let's get into major findings from the expedition, and what I'm going to do is just walk you through the sites that we drilled and talk about the major findings that were there. So the first site that we looked at was named U1506. So this was a site that we drilled on the northern Lord Howe Rise. So here's the Lord Howe Rise. So this was our northernmost site, and we're kind of really warm subtropical waters. And this site was drilled at 1,500 meters water depth. That's pretty shallow for a site to be drilled. The image that you're looking at now on the left side of the screen is called a seismic image. Basically what we do is take a ship, and it has this equipment that pulls behind it, and it's, to make it simple, it's taking a CAT scan of the upper part of the ocean crust. So it's sending down these waves, and that when those those energy waves hit a sediment or a surface with a changing velocity, it sends a signal back up to that ocean, or to that sensor that the boat is pulling behind it. So you essentially get this like profile of the upper part of the ocean's crust. It's very, very cool. So this really strong reflector right here is the seafloor, and all of that stuff above it is just the water column. That's just water. And you'll notice this really strange feature that is kind of here. Does everyone see it? It's kind of like bumpy, and there's like two big humps there, and it goes back down. We didn't know what that was. We had no idea, so we started taking guesses. A lot of people thought it was like a coral reef that had been drowned, or maybe basalt. Someone even thought it was a fairy castle. You know, we get on the ship, you get kind of goofy and be funny, but whatever. So we didn't actually know what we were going to drill into when we were drilling this. It turns out that this was basalt. So this is rock that is volcanic in origin, from volcanic activity, and it also is a type of rock that makes up the seafloor, the bottom of the seafloor. So what you're looking at on the left side, that's all sediment, that really light gray stuff. And where I have that pink arrow is where the sediment is in contact with that basalt, that volcanic rock. And there's three very cool things that we could observe from these rock flows. The first is that we have several volcanic flows or events that were recovered. So notice that this part of the basalt is very red in color, and it has a lot of modeling to it. That's because when that basalt was there, it was exposed to the environment. So it was exposed to wind, to rain, to the atmosphere, and it did what we call weathering. It started to break down. The basalt that's under it is very dark gray and fresh looking. That was not exposed to the elements. But then notice again, we have another top of a flow here where again, that was exposed to the elements, and then another flow happened, and then the top of that flow was exposed to the elements. So we have several flows, several volcanic events preserved in these cores. The second is that we have these large gas bubbles in the top of the flows. So that's why these things look very mottled, like these little holes in them. So that indicates that there is gas bubbles associated with the volcanic event, and that gas was escaping into the atmosphere. The third thing, and the best thing, was we found this feature called a Neptunian dike. That was in this core right here that I've highlighted now in pink. Right in the middle, there's this light feature that kind of cuts across the basalt. So what happened is, in this rock, there was this big opening, the seawater got into it, and it like formed kind of this like, we had mineralization formed, so a rock kind of formed in there. So my colleague was looking at this, and this is just a close-up cutout, and there's a heart. I thought it was super cute. Started to look at that Neptunian dike, and he goes, Adriane, I think there's fossils in there. And I'm like, no way. In the middle of a basalt and a volcanic flow? What? So we cut up the rock, and we sliced it very, very thin, and we put it under a microscope, and this is what we found. We did find fossils. So what you're looking at now, that's that Neptunian dike and where we took the cuts of rock from. So there's things like bryozoans. So we find those in our rocks around here today. They're still alive today. Ostracods, these are like tiny little, what we call seed shrimp. They're tiny arthropods. We found mollusks, so like bivalves. That big circular thing is green algae. That's another ostracod, the side of it. We found pellets, or just poop, and benthic foraminifera. And here's another mollusk shell right here, so like a seashell. All of these fossils indicate that those basalts were erupted into a very shallow water environment. That's a big deal. This site was drilled from 1,500 meters water depth. but those basalts indicate, and those fossils indicate, that that's a very shallow water environment like a lagoon or very coastal. So this was the kind of the big deal. So when I talked earlier about Zealandia becoming kind of sinking below the waves, what the basalts indicated to us is that at one time when these basalts were erupted, it had to be at or above sea level because those basalts indicate they were exposed to rain, to weather, to the atmosphere. Then there's sediment, there's seafloor sediments, deep sea sediments right above it. So going back to this is just a close-up image. You can kind of ignore that stuff over there, but this is kind of a close-up of that core section where the basalt is in contact with sediments from the seafloor. We think these volcanics were erupted when Zealandia was above sea level. The continent had not sunken below the waves. Around 45-50 million years ago, when that subduction zone started, the continent kind of got spread out or stretched, and that's when Zealandia sank below the waves. So our fossils indicated that the age of these fossils, or microfossils, indicated that the age of this Neptunian dike, we were able to get some other fossils out of here that told us the age of that, was the same age as this sediment right above it. They're about a couple million years separated. So this meant that as soon as these basalts erupted and that Tonga-Kermadec subduction zone started and stretched out the crust, Zealandia sank 1,500 meters below the waves within a couple million years. So that was a really big deal, So we actually figured out how Zealandia sank and the timing of it. We got really famous after this, and we didn't know it. We didn't know it. So we have to send out reports of what we find at every site we drill, and we didn't realize that the news stations were actually paying attention to what we were finding. So remember, that paper had been published in 2017 before we sailed. So Zealandia was a hot topic on everyone's mind. So when we actually drilled into it and we drilled basalt from that continent that was erupted on top of Zealandia before it sank below the waves, it got picked up by a lot of news networks. And we had no idea because we're at sea, we're busy, we're not plugged into the internet, we didn't know. So everyone was like paying attention and we're just like, yeah, cool. So our next stop was into Ranga Basin. So these are sites U1509 and U1508. So these again are very shallow water sites, relatively speaking. And this is another seismic image. So notice there's like this big reflector here at the surface. Again, there's that really dark reflector that's just a sediment-water interface. And then there's some of these features here, and it looks like the seafloor sediments have been crinkled or kind of stretched up. So we wanted to understand what was going on that caused that kind of compression of the sediments that make them kind of wavy, these folds and such. And we also wanted to recover sediment to infer the ancient climate of this area. So right around here off the northern part of Zealandia. I'm not going to show you a ton of what we found, but the coolest thing that we found were more fossils. So this was another site that was very close to the continental margin, so where we have a lot of shallow water organisms living, and those got preserved in the sediments. So we found, for example, crinoid fragments and echinoderm spines, things that would have been on sea urchins or starfish. Bivalve, this is a fish ear bone, it's called an otolith. We also found brachiopods, bryozoans, a tiny, tiny little gastropod. We also had someone on a ship, she was a paleontologist, and what she did was use hydrofluoric acid. It's one of the strongest acids you can use. And what she did was put hydrofluoric acid on the sediments that we drilled, so she dissolved everything out except for the organic material, like that remained. And this is what she found. There's insect remains, so pieces of insects that were there. She found phoriums, so this is a benthic foraminifera, the lining, the organic lining of that test. And she found pollen. So this is angiosperm pollen, so a flowering plant, and this is fern spore. She also found these weird things called dinocysts. Paleontologists aren't actually very sure what a dinocyst is. We think it's like a resting cyst of like an algae or something. But the pollen was the coolest thing. So these sediments were about 31.1 million years old. These fossils are about 31.1 million. This is what the Earth looked like at 31 million years ago. This is called the early Oligocene. Antarctica had ice. We had ice sheets down in the southern hemisphere, so the southern hemisphere was cold like today. Here's where Australia is, and here's where Zealandia were, so they were located, again, close to Antarctica. But because we were finding angiosperm pollen, these flowering plants, and the paleontologist who was sailing with us said that that was a very tropical species, And the fern spores, and if you think about ferns today, they don't come out until it's really warm, and they like very moist conditions. So we were able to interpret that during 31 million years ago, Zealandia was actually really warm, and it was actually a pretty moist climate. And that's all because we found these pollen spores and spores preserved in those sediments. So very, very warm climates during this time, even though Zealandia and New Zealand were located very further down, closer to Antarctica. But then a storm hit. So we're in the southern, we're very close to the Southern Ocean, where Antarctica is, and you have that big ocean that surrounds it. And there are major, major storms that come ripping out of the Southern Ocean and into the Tasman Sea. We had a storm come up, and it was predicted that we were going to get 50-foot waves where we were drilling. So we had to pull up the drill pipe very quickly and sail 320 nautical miles north to escape the storm. So what we did was called wowing, waiting on weather. So that sign, rough seas ahead, is what they put up on all the TV screens on the ship. They're like, secure your stuff, get out of the labs, don't go on deck, use caution, use handrails, do not go onto the bow. They put a duh after it, but I would have done it, whatever. But it did get really windy. So before we were able to get out of the storm's path, we did experience waves of about 20 feet. It was incredible. So here's us before they closed the deck. My friends and I were like, we've got to experience this. So we went on the very top of the ship and we were hanging on tight. And the wind was so strong, I couldn't even breathe. It just kind of rips your breath away. I've never experienced anything like it. And these are waves. It's hard to get a scale of it from this picture, but when you're standing on this kind of deck on the outside, the waves are down there, but they were coming up to here. So we experienced 20-foot waves. I did get a little seasick, so I didn't want to do that again, but then it was fine. It was also, when we got out of the storm's path, we found out it was our captain's birthday, and his name was Jack. So we threw a pirate-themed birthday party and a dance party for Captain Jack. Now, unfortunately, IODP doesn't allow the captain and the crew to fraternize with the scientists. So he couldn't come to his own birthday party, but we still had fun. So we grabbed a bunch of styrofoam stuff we used for drilling and for cores, and a bunch of other stuff, and we got creative and we made swords and stuff. We painted our faces. We just had a wonderful time. It was the coolest dance party. We actually have this major theater area on the ship. We also have a small library, so we opened up the theater room, put the couches away, got the black lights out, and blasted music. It was a wonderful time. It was much needed, too, in the middle of the expedition. You can imagine it gets kind of monotonous. Whoops. So the last site we went to was U1511. So this is down here on the abyssal plain. So this is outside the boundaries of Zealandia. So we were no longer drilling within Zealandia. We were drilling in 4,800 meters water depth. That's 3 miles water depth of water just before we reached the bottom of the seafloor. Really incredible. At these depths, those fossils that I work with don't preserve. When you put acid onto a seashell, calcium carbonate, it dissolves. The bottom of the ocean here is very acidic. Those bottom layers are very old, they're very cold, they will dissolve calcium carbonate like those shells. So when we pulled up these cores from 3 miles below the water surface, notice the color here. They were bright red in color. Does anyone want to guess why they were red in color? Yes, yes. What do you think? Crystals. Crystals! You're actually right too. You're both right. So, Australia is full of dust. This stuff comes ripping off the continent and gets deposited into the ocean. And some of that dust does contain iron. And iron mixes with water and it rusts. But I want to show you something that's really neat. So I've zoomed into this part of the core. So notice how it looks white and then it's green in the center. It's bleached. We weren't sure what that was. And there's also, I don't know if y'all can see it, can you see these little orange and yellow things in the very middle? Those are crystals of copper, natural copper. I would have never guessed that we would drill sediment cores and bring up copper. What we think happened, there's a lot of volcanic activity in this area that happened, not now, but in the geologic past. And we think there was hot water that was streaming through these sediments associated with that volcanic activity. And that hot water bleached those sediments, so that's why we get these white and green bands. And those waters, those volcanic waters, are full of ions. So copper is really associated with volcanic activity, so copper minerals started to grow in the sediments. Incredibly unreal. Here's another example of those bleached sediments where we have that inner layering of green and kind of grayish sediments with the red. So it was very puzzling. There was no fossils, but it was incredible nonetheless. So then it was time to head back to Hobart, Tasmania. That's a video of dolphins. I don't know if it will play. But they were like kind of jumping in front of the ship. It was very, very neat. And this is a photo of us coming back into port taken by my friend Brian Huber. Here's Brian. So this is our last epic selfie that we took on the Geology's Resolution. By this time, you go through a phase where you're like, oh, I can't stand these people anymore. And then you see port and you're like, oh, these people are my family. I don't want to leave them. I actually love these people. So we got off the ship. The first thing I ran to do was get a salad. I needed some fresh greens. You run out of those about 3 weeks after you board the ship. And then, of course, you go to a bar because you can't drink on the ship. And we had a great time. So this was all of us at that bar. And then we had another crossover party. There was an expedition getting on the ship after us. So this is my friend Brian Huber. He's a curator at the Smithsonian Museum. And this is my friend Ken McLeod. He's another paleontologist and another professor. Oh, there it goes. So you can see the dolphins that are leading us back into port, jumping in front of the ship and playing in the waves. We also saw sharks while we were out there. We saw a lot of squid and jellyfish coming up to the boat. So we do take our food waste and we put it into the ocean. We don't put plastics or any trash like that, things that will decompose, and that attracts those animals to us. So we actually did see a good bit of sea life while we were out there. A lot of seabirds as well. They're very common in the southern hemisphere. Okay. So just bringing this back home, like what we're doing now at Binghamton. So this, what we did, when I sailed, I was a PhD student, so I was really, really busy. So a lot of the research that we're continuing is continuing now at Binghamton. Okay, so the first thing we want to do is use the fossils that I study to infer ancient climates. So what you're looking at, this is a very complicated figure. I'm going to break it down. This is stable isotope. This is a geochemical curve, and we can use this geochemistry and convert it into temperature. So you're looking at a temperature curve over the past 66 million years. So there's just geologic time and our geologic lingo at the top, but at the bottom is millions of years ago before present. And this is atmospheric CO2 that we've reconstructed using different kind of techniques and methods through time. And you can see that this has changed. So a hothouse time is when the Earth was very hot. Atmospheric CO2 was in the thousands of parts per million. There were no ice at either of the poles. And then Earth started to cool down. We started to grow ice in Antarctica first, and later the northern hemisphere. The ice sheets began to really grow. We go into what we call an ice house world, and that's where we are today. We have substantial amounts of ice in the northern hemisphere and southern hemisphere. And then these are climate projections into the future. My students and I focus on this interval of time called the Middle Miocene. So this is when atmospheric CO2 was approaching about 500 parts per million. So it's where we're projected to go with respect to atmospheric CO2 concentrations in the very near future. So this is a really good analog time to see how our Earth systems will behave under increased warming and increased atmospheric CO2 concentrations. So what my students and I do, we focus on reconstructing the surface ocean. So how do currents change? How do they move under increased warming? And how do wind patterns change and shift across warming and cooling events? So we're focusing on site U1510 in the Middle Miocene section there. And what we're doing is using these fancy machines. So this is an X-ray fluorescent scanner. You can lay one of your core sections in there. So it's 1.5 meters long. You lay it in this cradle, and this machine will go along at like 1 or 2 centimeter intervals, and it will measure the amounts of elements that are in the sediments. And the elements that are there can tell you things about how windy it was during this time, or for example, how much carbonate is there, which relates to the amount of fossils that are there. So we can get all kinds of really, really cool data from this. The other thing that we're doing is using the chemistry of the fossils themselves, their tests. We can put them into a machine and acidify them and measure the different elements that are there in that Forium's tests, the fossil test. It's very, very cool. This is just some of our preliminary data. I don't think I'm going to explain it because we want to go look at the stars. But this is kind of what our geochemistry looks like. So this is the Miocene climate optimum when the world was very warm, about 500 parts per million. And we see this peak warmth, that there's a lot of changes. You can see just the squiggles change. So there's a lot of changes to the Earth system going on during this time. And we're also going to be using another technique to reconstruct temperature of the surface ocean using these fossils back in time. So here's just some more cuties. Trilobatus seculifer is one of the fossil species we work with. Okay, that's pretty much it. I just want to leave you with these few other images. This is one of 5 train engines. They were built in 1978 that powers the Geoides resolution. No, they don't make them anymore. If there's any part that breaks, we have to machine them. These are drill bits that are used in drilling. That's one of the volcanic islands around New Zealand. This is me bringing in a sediment core, and that's our entire expedition party right there. So feel free to ask me anything you'd like to. I also have pieces of Zealandia, the basalts that I was talking about, so you can see the piece that is like weathered, that was exposed to the elements, and one that's very fresh. So you can see the difference in them. I have my washed sediments up here, so all of those are little fossils. You can check them out. And then I have scoops of sediment from the cores themselves that are unprocessed, so you can kind of see them in the different colors and how they change. But coolest of all, I have an actual drill bit. So this drill bit screws onto the top of that thing, and it's used to drill into very soft sediments. And this thing used to have teeth on it. So we broke 15 of these in the ocean because we kept hitting these thin little layers of rock. So this is chert, just known as quartz, and we couldn't see those in those seismic reflectors, but these things were so tough, they broke the teeth of the drill bit. These things are about $16,000 a piece, and they just gave it to us because we ruined them. So anyway, that's that. Ask me anything. Feel free to come up and check this stuff out.
Right, if you have questions, I'll bring the microphone over so that our people on the live stream can hear. You have oh, we got a question right here. Excellent. What's your question?
Can break glass.
What?
Chert can break glass.
Chert can break glass.
Chert can break glass.
It can.
Yeah.
It can. Actually, it is a type of glass. It can break glass. That's good. Nice.
So right now, climate change is because of man.
Mm-hmm.
But millions of years ago, we weren't around.
Mm-hmm.
So as you research, have you discovered what causes different climate change?
Yeah, that's a good question. I don't research the causes of it. So during the Middle Miocene, we know that climate event, when the Earth got really warm, like 500 parts per million CO2, that was actually caused by a volcanic event, a massive volcanic event called the Columbia River basalts. So this was a massive volcanic event that took place on land, and with volcanic events you get a lot of gases that are associated with that. So you can get a lot of CO2 and methane that are released along with some other things. But it's those greenhouse gases, carbon dioxide, CO2, and methane, that really warm the Earth. So those are keeping Earth's sunlight, that energy from the sunlight, trapped within the Earth system, within the atmosphere, and that's what's causing the warming. So yeah, that's a great question. And we also have other events in the geologic past. In fact, of the 5 major mass extinctions, we think that most of them, except for the end Cretaceous, 4 of them were caused by massive volcanic events. They warmed the Earth so fast and so much that caused a lot of other effects to happen, like the oceans to become acidic and things like that, that led to mass extinction events too, and major changes to our climate system.
Any other question? Got a question in the back here, so give me a second.
I'm afraid. Did you realize that that last graph with the heat wave?
That one?
Yeah, that really explains why Harley Davidson isn't making an electric motorcycle. Did you ever think of that?
Why Harley Davidson is not making an electric motorcycle? I had not thought of that.
It's like the waveform of country song.
Yeah.
All right.
That's fair.
All right.
On your samples, you had found copper. Have you ever found gold or diamonds from the volcanic activity?
If I did, I would not be here today. So no, I haven't. No, those form in a lot of different processes. Diamonds form under immense pressure and heat. And in fact, a lot of diamonds that we produce today are lab created. And the other one, gold, isn't really found in deep sea sediments. That's more associated with like in California, I was just hearing they're going to get like a second gold rush happening because they have so much water that's melting now from the snowpack from the season that's washing out all of the gold that's contained in that continental crust. So gold forms mainly in continental crust, not the basalts, like these rocks that make up the bottom of the seafloor. They don't have the right chemistry, but that would be incredibly cool.
I have a question. So as you're going and drilling down, and I guess you do like one entire. You show that series of cores.
Mm-hmm.
Is that all from one pull, as it were?
Yeah, so when we go down and we collect a core, it's in 10-meter sections. So we go 10 meters down, pull it up, wipe it down on the core deck, the technicians do, and they cut it into 1.5-meter sections.
Mm-hmm.
So what you were looking at were not just one core. I don't know if this will go back far enough. Well, we can look at this. Like those.
Yeah.
You're looking at a core that's cut into sections, so 1.5-meter sections. So we get about 6 or 7 of them, depending on how much sediment or rock we recover. So in the beginning, you were looking at about 1.5 cores worth of sediment and rock.
So then, when you've done your core, how long does it take to sort of bring it all? Because I'm assuming you have to bring the whole rig back
Yeah.
up again.
Not the whole, yeah, so we keep the drill string down in the drill bit, but what we do when we're ready to bring it up, we have a core liner, so that's like the plastic liner that these stay in, and that's how you can kind of see it here. It's right here.
Right.
So they're in this like thin core liner, and that's how we store them in the core repositories. There's 3 around the world. We bring them up, we cut them.
But as far as
Yeah.
the amount of time it takes to bring the core back up.
Yeah, I'm trying to think. So it really depends on the water depth. Here we were drilling in 3 miles, so it took a good amount of time. I'm trying to say like an hour, 2 hours to pull these back up.
Mm-hmm.
But in really shallow water, we can have a core coming up like every 20 to 30 minutes, which gets really stressful. Because every core that we pull up, the paleontologists we go out, we take a cereal bowl out, and the technicians take apart the core, and we get the last like 10 centimeters of that core. And then we take it back to our lab and wash it and process it for our fossil, so it looks a lot like this, and put it under a microscope. So we have to do that like every 20 to 30 minutes. When we have cores coming up about every hour, 2 hours, it's much more manageable. So it depends a lot on the water depth, too, that we're drilling into.
Interesting. Any other questions? We got one over here.
You talked about a massive volcanic event. What would that compare to, like the volcanoes we have in Hawaii today?
Yeah, it's not comparable at all. So the Hawaii volcanoes, they erupt every now and then, but we're talking about like a massive amount of land that was covered by volcanic material. So for example, I just taught my class paleobiology, and we talk about the mass extinctions. And in the end Cretaceous mass extinction, related to that was a massive volcanic event. These were called the Deccan traps. So the Deccan traps erupted on western India, and if you like split the continent into force, it took up almost a quarter of the entire continent. And it also erupted into the ocean. The Deccan volcanics today are about 1.5 miles thick, and they are incredibly massive. So these are things that we're talking about on the scale of like volcanic events that would cover multiple states in the US today, if not more. So our little volcanoes are nothing compared to like these monsters that have erupted in the past. It's a good question.
We do have a question from the live stream.
Okay, cool.
From actually one of our previous presenters here, Peter Klimas. They ask, about when was Zealandia submerged under the sea?
Ooh, so Zealandia was submerged under the sea probably it was around in the Middle Eocene, so about 49, 50 million years ago. So that's when that subduction zone started, Zealandia got stretched out, and it started to sink below the waves. So yeah, that's a good question. I could get into an entire lecture on the sinking of Zealandia itself. It's really, really a cool process that happened. Really unique process.
They did sort of have a follow-up as well. They wanted
Sure.
to confirm that the submersion of the continent of Zealandia occurred around the same time as the volcanic activity.
No, as which volcanic activity?
They did not specify.
So we had the sinking of Zealandia that was associated with that subduction zone that started here. If they're talking about the Middle Miocene stuff, that happened much, much later. Yeah. So Zealandia sank around here, 40 million years ago. But we look at climate from about 15 million years ago. So there was a major, the Deccan traps I was just talking about, those took place here and then back. They had been erupting for a long time. They didn't cause the mass extinction, but they were happening before it and during it. And then there was the Columbia River basalts that happened here at about 15 million. So the sinking of Zealandia is actually bracketed by 2 major volcanic eruption events, but it wasn't caused by it or wasn't really associated with that.
All right, very good.
Yeah.
Well, unless there's some other questions, or if you have some other questions, I know Dr. Lamb, this is her first time up here, so she can't leave until she looks through a telescope.
I'm not leaving until
So, first of all, thank you very much for an excellent presentation.
You're welcome. Thank you all.
And so, Mark, if I could have you, the moon will be coming up fairly soon. Well, the moon is technically above the horizon, and we just need to get it above our horizon of the trees. So if I could have you on the 6th. We have one of our other scopes that's out in the yard. We'll be looking at Venus and Mars. And, of course, in about 20 minutes or so, 20, 25 minutes, the Starlink train should be coming by, and we'll get a chance to check that out. So next week we have a group of high school students that have a competition robot, and it's not one of the ones that like eats the other robots. These are more of they do work in teams, and they have certain tasks that they have to perform. It's called the Southern Tier Robotics Club or something like that, and they will bring their robot here, and it'll be it's actually quite neat to see these high school students doing some pretty neat stuff. And then we'll go back to astronomy again, and the following week we'll actually have one of our educators, Robert Olaf Seegers, will talk about Neptune and the planet Neptune. So I would love to see you back here, and if you can't make it here in person, you're always welcome to watch us on the live stream. So thanks again. And thank you all for coming.